Hello everyone and welcome to the next webinar series. This is Aparna Deshmukh, Technical Director with Next, and I will be your moderator for today's session. So we are excited to dive into our today's webinar titled Design of FRP Pultruded Structures, Why, What, How. For continuing education credit, attendance for the entire duration of today's live webinar will earn you a certificate of completion of 1 PDH. Your certificate will be available in ACI University under the certificate tabs within 2 days. For those who cannot join us live, the on-demand recording will be made available about a week after the live presentation. ACI is an approved education provider for the American Institute of Architects and the International Code Council, and this webinar has been approved for one learning unit. Please take note of our disclaimer on the screen for the next webinar series. So let's look into the description of our today's webinar. This presentation will focus on the design of FRP pultruded elements based on ASCE SEI 74, covering key benefits, applications, and design considerations. It will provide an overview of similarities and differences between FRP and steel, along with practical design and construction examples to enhance understanding of FRP structural systems. Our learning objectives for this webinar are as shown on the screen. Now let's welcome and introduce our today's speaker. We have 5 speakers, starting with Francisco Di Caso. He is the principal scientist at University of Miami. We have Kevin Walsh. He is the principal engineering at FOST Engineering, and he is also an associate professor in Department of Civil and Environmental Engineering at University of Notre Dame. We also have Juan Diego Pozo. He is a senior structural engineer at Frost Engineering and Consulting. We have David Pircio as a project engineer for Frost Engineering and Consulting. And at last but not the least, we have Ehsan Hariti, a PhD student at University of Miami. So I'll hand it over to our speakers and let's listen to their presentation.
Thank you very much, Aparna, and thank you everybody for joining us today. I'm really delighted to have and be able to speak with such esteemed colleagues on hopefully there's not new or novel or innovative material. I think that's the first thing I want to highlight. And let's understand primarily why we need to use FRP pultruded elements. This slide gives you an overview of the evolution this has had. I should say that its evolution also predates this with much use in the aerospace industry. But if I were to focus primarily on 2 main things of why now is the time to spec, use, and develop pultruded FRP elements are these 2 magnificent tools. The ASCE 74 load and resistant factor design for pultruded FRP elements, which was published just last year, and our European counterparts published in 2022, the CNTS 19101. Those are 2 very strong documents that give the necessary both confidence as well as support to engineers, specifiers, and users in order to move forward. I would want to highlight that those documents, even though FRP, as many of you, is made from your resin and your fiber, embedded in this matrix, that those documents primarily look at the areas highlighted in red. So these are thermoset resins, right, with glass or carbon systems. And within the thermoset resins, they only refer to vinyl ester, polyester, and epoxy type of resins, right? And that the product that you have will need to meet the different environmental factors that it might have based on those. Pardon me. Let me go back based on those needs for that specific application, and that understanding both the type of fiber and the type of resin composition that you have on your pultruded element needs to be matched with that structural application. And if you're not too familiar with the pultrusion process, this slide gives you an overview of what it is. Pultrusion, because you're pulling those fibers through, not unlike other FRP type of systems. And as you pass those fibers through it, the saturating resin, and you align them, and you have this constant tension of the fibers. On the other side, very important, goes through basically an oven where the resin is baked. That resin structure crystallizes in order to give the FRP pultruded element those structural properties. The resin transfers those loads into the fibers, and then you have that mold at the end of the process that gives basically the cross-sectional shape. So pultrusion works great as long as you have a constant cross section, right? A continuous constant cross section. And that is key. And hopefully you can start thinking of where in civil and structural engineering do you see constant cross sections of structural elements. So this gives you an overview. And even though I have on the bottom left corner FRP rebars that are also made through the pultrusion process, these tend to be inserted inside of concrete as a concrete reinforcement. Today's presentation really focuses on all the other items. These are ready-to-use structural shapes, channels, gratings, panels, tubes that are used as a finished element in construction, not with concrete. So let's think of those areas where we can use them and why to use them. A lot of it is because of these are non-metallic materials. Right, so corrosion and chemical resistance tends to be a driving factor in many of these applications. But as my colleague will later show on some of the case studies, there are many other driving factors, primarily the low maintenance and the lightweight, that are really starting to drive that need. And these tend to be maybe key or niche applications, but it's starting to grow. And the last item is electromagnetic transparency, as we will see. That is also a driving element in many of the projects that are seeing this type of elements being used or that have been used for the past years. But beyond construction and infrastructure, it is important to highlight that many industries are using and continue using FRP pultruded elements. And this is important to acknowledge because it gives confidence. It continues the development, quality production, and specifications of these different materials in these different industries. And I think we tend to be maybe the late adopters on quote unquote innovation. So as a construction and a structural infrastructure industry, we can learn from those industries, borrow a lot of what they're doing, and then implement them in our sites. So important to be aware of that. And as we do a dissection within our infrastructure sector, really there's many small, large, medium scale type of applications where they're being used. On the top, you have a summary of those major applications, and on the bottom, you have what the competing materials are in this type of application. So even though in many of these applications, we do see other metallic materials as well as non-metallic, such as timber or wood, composites really go across the entire gamut of all these, where many times there might be a niche application that drives the factor, but as hopefully you'll learn today, there are more other driving factors. And that being said, I want to pass it on to my colleague, Hexan, that will continue on what FRP pultruded elements are in this presentation. Thank you.
Hi everyone, thank you, Dr. Dicasso. And as we move to the what section, let's explore what makes pultruded materials unique and how they compare to conventional construction materials. This slide highlights the material properties of pultruded FRP compared to the steel, aluminum, and wood. FRP, as you can see, is incredibly lightweight, and for instance, its density is around 5 times lower than steel, making it ideal for application where weight reduction is crucial. And I have to mention that all these values are based on the ASCE 74, and this value might vary depending on the specific manufacturer. And about the tensile strength, FRP is around 30 KSI, and which is almost the same as a steel A360. And however, the key difference lies in the Young modulus and shear modulus. FRP Young modulus is around 3000 KSI, which is about 10 times lower than steel. Which is 30,000 KSI. This lower stiffness is why deflection control often governs FRP design, and rather than simply focusing on the strength. Okay. Uh, Design with the Pultruded FRP introduced unique challenges. First, the balance between the stiffness and strength. While FRP handles impressive loads, design are often governed by deflection limit due to lower stiffness. And second, FRP anisotropic or orthotropic nature and makes its properties direction dependent, and it has a high strength along the fiber direction, but significantly lower strength in other direction. And so we have to mindful about of load distribution along the fiber and the cross shape. And finally, creep and potential creep rupture present long-term challenges. FRP can deform under the sustained loads and potentially leading to failure if this affected are not accounted for design. A new standard ASCE 74 uses the load and resistance factor design or LRFD approach to account for FRP unique behavior. This methodology helps ensure structural reliability by factoring in variation in load and material properties. Environment and the time defect factor also play a crucial role in the design, and FRP can affected by a long-term exposure to the moisture and temperature changes and creep. And additionally, FRP reliability in bending, compression, and shear must be compressive addressed in our design. Moving on to the how of FRP design, we refer to ASCE 74, which is published in last year into 2023. And this standard provides a structure approach to design FRP structure elements. The standard contains 9 core chapters covering essential design area like tension and compression member for flexion and shear and connection. And additionally, it has a section for seismic design and 2 appendix for glossary and symbols, and 9 chapters of commentary. And they are not mandatory, but the first 9 chapters are mandatory. About the design application goal of the ASCE 74, Pultruded FRP find application in new building, prefabricate component and structure exposed to harsh environments, and such as industrial facility and bridges. And it's particularly beneficial in seismic zone thanks to high strength to weight ratio. And in corrosive area environment, where is significantly outperform traditional or conventional material like steel. At the core of ASCE 74 is a fundamental design equation. As you can see in this slide, R sub U represents the required strength based on the factored load and should be equal or less than R sub N, which is nominal strength of the structures. And we have a term of the lambda and O represent the time effect factors and the resistance factors. And the first one, time effect factors, account for material behavior under the sustained load, and the second one, resistance factor, address the inherent variability in FRP properties and adding an extra layer of reliability to our design calculation. In this slide, I brought the design equation for an I-shaped pultruded FRP beam, and in this design we consider in the design of FRP pultruded we consider not only the material rupture, and we also various type of buckling, including global buckling like a lateral torsional buckling and along the pultruded FRP member, and local buckling in the flange and web. In the steel design, maybe you might be familiar with, we have a compact section ensure the local buckling in flange and web occurs only after reaching the plastic moment capacity. However, for FRP, we have a thin wall like I-shaped tube, and so require a specific equation for local buckling for flanges and web. And before handing the podium over to David and wrapping up my section, I'd like to emphasize the simplicity of the designing FRP Pultruded structures. Global buckling in FRP might be complex, but as you can see, we just have a same equation in the steel structures. I brought this from ASCE 360, and you can see how the equation are similar. And in the FRP, we have a direction dependent properties like a module of elasticity. So we have use a longitudinal module of elasticity or longitudinal shear module of elasticity. And what I'm trying to say that designing with the FRP isn't as complex as it might seem, and it's actually quite similar to working with the conventional material and very easy to understand. Thank you, David.
Thank you, Hassan, and thank you everyone for being here today. My name is David Birke. I will walk you through towards the connection design instead. So as Hassan mentioned, the design of members is really very similar to steel or other traditional material. Is quite straightforward, I would say. Now, I don't know if you ever heard this sentence, but for FRP, the devil is really in the details when it comes to the design of connections. So when it comes to connection, we have several limit states that we need to address. I'm showing it here, the breakdown of all of them. Some of them you might already be familiar with if you have worked with steel or designed anything in steel before. We have the typical bearing limit state. We have some sort of net tension limit state, shear out, and block shear. Some others are more peculiar to FRP, like the cleavage limit state or the pull-through limit state due to the anisotropic behavior of FRP itself. When it comes to the resistance factor, the phi factor mentioned previously by Hassan, there is a big distinction, a clarification that has to be made in terms of comparison with other material. You can see in this table here that typically the resistance factor for FRP are significantly lower than the ones for similar type of design like hot roll steel or cold form steel. This, of course, is due to multiple reasons, but I would say the primary ones is that we have to remember that FRP is a brittle material, so it doesn't perform the same degree of ductility that steel instead has inherently as a material. So to account for that, of course, we need a larger factor of safety that resolves itself in a lower phi factor, as well as relatively FRPs are relatively young material. I say relatively because, as Francisco mentioned before, it's been around for a while, but the amount of testing that has been performed on FRP type of connections is, of course, in total amount much lower than when compared with other materials, and this gives us the necessity to be more conservative when developing resistance factor for the material itself. Another thing to keep in mind and to bear in mind when coming to design of FRP connection is that, as mentioned by Yasin before, the material itself is an anisotropic material, meaning that in different directions it would have different stiffness and, more importantly, for connection strength as well. So we have to account for it, and the code, of course, ACI 74, as well as the European counterpart, account for that difference in strength among different directions. And very much so when it comes to connection, it becomes a matter of defining properly which are our parameters, because they will be dependent on the direction of the force. For example, here on the image on the top right, you can see the various geometrical parameters of a simple connection. When the direction of the force, like in this case, is horizontal, our S, so our pitch distance, our G, gauge distance, E1 and E2 are as shown in this figure. But if we are reversing the direction of the force, we also have to reverse the definition of our geometry. So what before was G will become S. what before was E1 will become E2, and so on and so forth. Given that the amount of limit states that we have to check, and given that different interfaces of our connection might have different direction of pultrusion, we end up having to check typically around 6 limit states for each interface. So if we are thinking at a beam to column, simply supported connection with angle clips, we are looking at 6 limit states for each interface, and the one for beam to clip, the one for the clip to the beam, the one for the clip to the column, and the one for the column to the clip. So for a total of 24 checks that we need to perform. And to give a visual representation of this exemplary, this example connection, here I have a sketch of a typical beam to column type of connection, again with angle clips attached to the beam and to the column. So for a simple shear condition, what we have to imagine is that the shear vertical on the beam will be perpendicular to the main direction of the fibers, while on the clip will be parallel to it, and again parallel to it on the column. So to design an FRP connection, a very critical step and the very first step to take is to determine the geometry and the relevant parameters and force direction on each interface. So here you can see a breakdown of the 4 interfaces of this connection, each one of them with their own specific force direction, with their own specific pitch and gauge dimensions, and then the distance dimension, as well as the forces to be captured on each one of these interfaces. Once you've done that, you can start determining your strength and demand capacity ratio on each one of these interface. This is a very quick example given for just one single limit state for one single interface. For the shear out limit states, one of the limit states that we were seeing in the previous slides. The equation, again, they are very similar to the one of steel connection, for which shear out is another is a limit state that exists as well. What we have to account for FRP are all these factors called environmental factor, like CM, the coefficient of moisture, or CT, the coefficient of temperature, that we have to use to adjust our strength on top of using our resistance factor and our lambda, the time effect factor, the one that takes into account for the creep behavior of FRP. Now, once you have set up your equations, it becomes fairly straightforward to repeat the same process for multiple interfaces. So, of course, it's not something that you might want or might necessarily enjoy to handle by hand. So you typically try to develop spreadsheet in order to support your design. And so, as I mentioned, when you complete your calculation for each one of the limit states and each one of the interfaces, you might end up with a table of the like of this one, in which you have 6 limit states for each interface, 4 interface. We end up with the 24 limit states that we were mentioning before. Again, this is something that most likely you want to automatize. It's not something that should scare when approaching the design. Of course, might result a bit more complex or more long rather than complex, just because of the different interfaces and the anisotropicity of FRP that needs to be taken into account. But once you have set up your own spreadsheets or your own calculation methods, is something that you can repeat very easily for different configuration. And now I will give the stage to my colleague.
Yep. So our team has been the engineer of record on about 200 unique Pultruded FRP projects at this point across the country and a few internationally. We are not going to be able to cover all those projects here, but we do want to give the audience a taste of what is possible with Pultruded FRP in ways that you might not have thought of. So this first project is an FRP canopy structure, serves as basically parking canopies, and then solar panels will eventually be put on top. You're seeing the product as it was, I think, earlier this week. So it's still under construction right now in New Jersey. The cold form steel you see going left to right on the left picture there is obviously metal. Almost all the rest of it is FRP. So the 24-foot cantilevering beams that are coming out are all FRP. The columns are FRP lattice work with some cladding on them. Reinforced concrete bases, obviously, but those are reinforced with FRP rebar. So the goal here was to have a product that could be fabricated easily, shipped easily because it's lightweight, and it's very corrosion resistant, given that it's mostly FRP with a little bit of light gauge steel on top. This was, despite it looking somewhat simple, it was quite a complicated structure. FRP does have a lower modulus than steel, meaning it's not as stiff. This type of structure is already vulnerable to being dynamically sensitive, particularly to wind loads. So it was a complicated analysis, but we're very proud of it. There's a lot of buildings that we've done with FRP more recently. This is an example via North Star, who our colleagues in North Star are down in Florida. For anybody who's particularly interested in coastal housing in the Gulf and its resistance to storm surges and wind, Paul Inglese, who's the CEO of North Star, is going to be presenting in Chicago at the North American Pultrusion Conference, giving a keynote on this very subject. So huge potential here. The great thing about FRP is that it's corrosion resistant. Even if it gets wet, so long as you air it out, you're not going to have the issues that you might have with other traditional materials once they get water saturated due to flooding or storm surge. Yep. This is a multi-story structure real close to the fault line in Santa Clara, California. Everything you see in these photos here is pultruded FRP with the exception of the bolts. So this is the largest by mass pultruded FRP structure in a region of high seismicity in the world, of which we're aware. There are some that are a little bit larger in regions of lower seismicity. Our team actually won an award through the CAMX conference for this project a few years ago. Now, corrosion resistance was not a particular concern to the owner on this one. They're targeting 25-year service life at the most anyway. The reason pultruded FRP came into this project is because getting the labor and the material for this structure to be steel was going to take 3 times longer than the FRP. So we actually had the FRP on site constructed with the team having walked away by the time the steel would have hit the fabrication shop. So this was all about speed and availability of materials and labor to get the job done very quickly. This was in an infrastructure yard at a data center. That's a very fast moving industry. They've even coined the term mission critical. So they were moving very quickly. In addition to the high seismic requirements, you had some unique detailing at the connections. We actually had to develop a prying equation for the FRP connections. We did this project before the consensus standard ASCE 74 came out earlier this year. In the new ASCE 74, there are seismic design coefficients that fall in line with what you might expect from ASCE 7 for any of those of you who are structural engineers and practice in that space. This is a project that's still under construction right now. This is at the University of Arizona. In their biosphere, they have an indoor saltwater ocean where they've been carrying out research on coral reef growth for decades now. It's a very hot environment and very moist. Despite it being in the desert, they're not getting enough sun on the coral. That amazed me, but I'm not a glazing expert, so they have some sort of issue there. As a result, they wanted trusses spanning 60 feet over the indoor ocean there with some UV lights that they could use to better grow the coral. Again, the issue is corrosion resistance here. They did consider some sort of stainless steel, but again, availability of material and labor for that just was cost prohibitive. So they asked us to design it out of pultruded FRP. They're only going to be able to take out a small portion of the glazing structure that you see on the left side of the top left photo there. So it does have to come into 3 parts. It's going to have to be spliced basically up in the air. We're coming down on some very narrow parts of their artificial seawall, a bit outside the scope of this presentation, but we also use this project as a wonderful example of the importance of getting a high resolution laser scan of existing structures so that we could land some columns in very, very tight spaces here. Great. Wrapping it up here, this is another recent award winner, at the most recent CAMX conference, or sorry, it was a finalist, didn't quite win. This is at the University of Notre Dame. And Notre Dame built really their first lakeside park-like structure in their 180-year history. This is right across the street from the grotto for anybody who's familiar with the campus sitting on Lake St. Mary's. The architect laid out the site to look like the decades of the Rosary, given the Catholic tradition at the University of Notre Dame. And there were 2 primary structures in which our team was involved. The first is the boardwalk that's going out into the water. Our team are full service structural engineers. We will design with any material. We're not necessarily pro FRP. We just use it as a tool to solve a lot of problems, and it helped us out and helped our client out a lot in this regard. The client, University of Notre Dame, sets a minimum of 100-year service life for effectively everything they build on campus. We asked at the project kickoff, again, when the schematic was assuming steel from the architect, if maintenance was going to continue dumping salt here. We have our first snowfall of the day here in South Bend, Indiana. We get a lot of snow and ice, and there's obviously a lot of concern about walking paths at the University of Notre Dame so students and faculty don't slip and get hurt. And the answer was yes, maintenance probably will be dumping salt directly on the structure. And if for some reason they decide not to do it directly on the structure, they're going to dump it right next and people will just track it on there. So we were very highly worried about corrosion on steel framing if we're targeting 100-year service life. So we made the argument that we wanted to use Pultruded FRP framing. Obviously, it's a bit difficult to camber those horizontally or curve them horizontally. So we did end up laying this out sort of multilinearly, but it worked out really well. The framing is underneath some very nice Kebony, as I understand it, artificial ebony boardwalk. It turned out very nicely, and it's sitting on top of some helical piles that were drilled down into the lake muck from the shore side. The other structure of interest is that infinity fountain. That infinity fountain is can only suffer an 1/8 inch differential settlement over its service life before the water doesn't flow out on all sides like it's supposed to. So that infinity fountain and the walking pavers around it, on which Notre Dame spent a very pretty penny, are sitting on a 70-foot diameter, 18-inch thick mat foundation, which itself is sitting on 39 drilled piers that go down to 65 feet. This entire site is sitting on some very highly compressible and expandable clay marl, is what we call it here locally. And the geotechnical engineer on the project insisted that we go all the way down to better soils below. All of that mat foundation underneath this fountain is reinforced with Pultruded FRP rebar. So two types of FRP on this project, even though they're both kind of buried and hidden, but we're very proud of it. And a great application of an outdoor space where corrosion resistance for a long service life was absolutely necessary. I'll hand it back to you, Aparna.
Thank you all. Thank you all the speakers, and thank you, Kevin, for this wonderful, case studies. I think those were impressive. With this, we open our question answer session. If audience, please submit your question in the question box. We have few questions. So the first question is, how do you compare pultruded shapes with steel? Firstly on cost and second on sustainability. Anyone could answer. I mean, it's not.
I think I can take that question. So in terms of pultruded profiles, the profiles, let's start with saying that more or less around the industry, it has been reached some sort of consensus on some standardized shapes. So most of manufacturer will now have standard profile that they keep on stock so that you can have an off-the-shelf type of solution for yourself without having to go towards customizable type of pultruded shape. So that helps bringing down the cost. Nonetheless, when it comes to the raw material cost, is typically FRP is typically more expensive than steel, but it counterbalance that expense when it comes to installation, because being much lighter, it helps keeping very significantly lower the cost of installation, transportation, and shipping. And to answer the second part of the question instead, we have a reverse situation when it comes to carbon footprint, in which FRP is actually a much better solution in terms of environmental sustainability. The entire process, manufacturing process, as well as shipping and installation, it typically brings FRP as a much better solution in terms of environmental sustainability with comparisons that I've seen some research available on that, and we can maybe leave some a link after the presentation regarding that, with carbon footprint that is typically 40 to 60% lower when compared with steel, especially for and it gets even lower when accounting for the entire life cycle of the material itself,
Mhm.
as FRP does not require high maintenance for corrosion purposes as well.
Great, thank you. Our next question is, which resins were used in FRP for the data presented throughout? Also, why was that resin chosen?
I'm assuming these are for the design examples. Maybe Kevin, you wanna? I would assume these are typically epoxy or vinyl ester, but different
That
manufacturers use different resins. David or Kevin?
yeah, Kevin, or I can take it as well, whatever you prefer.
David, I'm going to let you speak to that. The short answer is availability and cost, but I'll let David talk about where vinyl ester is used.
Yes, most of the resins used in the project that you have seen, they are typically polyester or vinyl ester, with with a strong preference towards polyester from our client perspective, just because it costs significantly less than vinyl ester. Vinyl ester can be we can specify it when we have more stringent requirement in terms of temperature resistance. Vinyl ester is typically more resistant to temperature effect than polyester, and for some very aggressive chemical environments, for which vinyl ester again present a larger resistance than polyester. But in general, what we specify is a polyester resin, just because it matter, given that strength and stiffness are very similar among the two materials, the cost is the driving factor there, and polyester is typically much cheaper. And even if this was not specifically asked, just to complete an assessment of the material there, for the fibers, if you're curious about that, they typically are glass fibers, the one that are the most commonly used in design. Although you can have some carbon fiber elements as well when you require a much larger stiffness.
Yeah, I want to follow up on that by sharing it's not a project that we showed in our slides, but we are in the process of constructing an inverted 20-foot tower in a chlorine tank in West Virginia, basically where chlorine and other similar products are made. And in that case, we did have to upgrade the product from a more common and cheaper polyester to a vinyl ester resin.
Mhm. So is just a follow-up to this. So is this based on ASTM specifications, and ASCE? Does it comply with ASTM, or it is project by project basis? The reason I was asking this
Sure.
with the
D-
resins. Yeah.
David, would it be okay if I took this one?
Go ahead.
Yeah, this is the question that comes up from the industry quite a bit, and I think it shows a juxtaposition between sort of the manufacturers of these materials and how the construction industry thinks. So on our side is the specifiers of material. Now, obviously, we have a relationship with certain manufacturers, especially if they bring us the project. We're going to be specifying their product. But generally, when the project comes from a client who doesn't have a particular, dog in the fight of manufacturers, we're specifying minimum material properties, just like we would with any other material, concrete, steel, wood, whatever. And we don't really care where it comes from, so long as material properties are met. ASCE 74, that new consensus standard I mentioned, LRFD design of Pultruded FRP structures, does lay out minimum material strengths as well as the associated ASTM standards. There are still some gaps there, and we're working on some R&D efforts with the industry to fill those in. But they're almost all the way there. So at this point, Pultruded FRP for the construction realm is really treated just like steel, for example, which is good, because that's the only way to get it for us to invest putting it into built infrastructure en masse right now.
Okay, great. Thank you. Our next question is, the bolts used for connections are steel bolts or stainless steel bolts?
I think I can take that one. So it again very much depends on the final objective of the project. So if we are looking at that project example for the boardwalk in the University of Notre Dame, those are stainless steel balls. That was a choice related to the fact that we wanted to achieve that 100 years of service life. So steel balls might have not, normal steel balls might have not met those requirements. In general, what we specify for the structures are standard ASTM A325 bolts, so no stainless steel bolts, unless specifically required by the client. There are also options to have FRP bolts. They do exist. They are available in the market, especially for if longevity or electromagnetic transparency is a primary issue there, so that you can have an entire structure that is non-metallic down to the bolts. Problems with those bolts is that are typically present a lower strength, a significantly lower strength than steel bolts. So we tend to specify them just when required. Another follow-up on that questions is that typically steel bolts in the connections, they are not the governing factor, are typically the other limit states on the FRP material. So even having a partial loss of cross-section due to corrosion of the steel bolts typically do not endanger the structure at all, because the demand to capacity ratio on the steel bolts are very low in most of the cases.
Great, thank you. We have a follow-up question on the resin question. It says, how much of the cost of FRP is the resin? Isn't 80% GF? I think GF is glass fibers. I don't know.
I actually can take that one because I just had a conversation a few days back with some of the manufacturers, so I have a more or less precise answer to that question.
Sure.
Typically, the resins are varying between the 15 to 25% of the cost of the total material as pultruded. So there is, of course, cost for the fibers, cost for the setup of the pultrusion process and whatnot. In all that, in all those items, typically the resin covers more or less between the 15 and the 25% of the cost.
Okay, great. Our next question is regarding the fire ratings. So what is the fire rating of the material, and are they treated as steel elements?
I'll start with answering this question, and then I'm going to let David follow up and correct me on anything. This is the other hot issue in the field right now, pun fully intended, as Aparna well knows. So when we've been asked by regulators in the past to, prove the fire rating, they typically view it more as wood, which, to be honest, is appropriate in terms of material makeup. It's closer to wood than steel. However, while the manufacturers will say it's not flammable, it will burn, the resin will burn. However, pultruded FRP, when it burns, does not add heat to a fire like wood does. So I guess, pound for pound, it's better off than wood structures. With that said, the issue that we face is before it even catches on fire, it loses strength and stiffness due to heat. Now, any material will do that, but FRP is potentially vulnerable to that. So it's an area of work that structural engineers are becoming more and more responsible for, especially as heavy mass timber becomes more common. 20 years ago, very few structural engineers would have thought of really the fire rating. That's the architect's problem, right? Or the regulator's problem. Now it's becoming our problem, and it is an issue with FRP. What I will say is as of now, you're really no worse off with FRP than you are with a wood structure. And if you need to insulate it, oversize it, you can. There are options there, just like you have for wood.
And if I can follow up on that, on a tangential topic, when we say that temperature is affecting FRP, we are talking of temperatures that are well above what is human sustainable. So we are talking of temperature above 150 Fahrenheit degrees. So if you have sustained and keyword being sustained there, temperature that are well above 100, 120, or even above 150 Fahrenheit. At that point, you might want to consider to have insulations there. Environmental variation are typically acceptable. So even if in a very hot summer in Texas, you exceed the 100 or 110 Fahrenheit threshold, once night come and temperature goes down, FRP recovers. There are tests that have shown that FRP recovers basically all of its strength. But when it comes to sustained temperature for a very long period above a certain threshold, and it's when you want to have a layer of insulation for protecting the material.
Great, thank you. Our next question is, does AC 74 talks about fire or seismic? If not, then what are the provisions and how one should deal with it?
Seismic, yes. The information is still not quite as advanced as it is for a lot of other traditional materials, so we still have more work to do in that space, but basic seismic design coefficients are in ASCE 74. For anybody who is a structural engineer, you'll be familiar with the R factor. They tend to be low for FRP. So we're not getting up into the 4, 6, 8 range like we are for highly ductily designed material with steel. Now, the good news is in regions of high seismicity, it's very lightweight. So in terms of the dead weight of the structure, you have a fraction of what you would with a steel structure. Does that balance out? It depends on the structure. But we made the project I showed you work basically on top of the fault line in Santa Clara. So we have not seen seismicity as being a huge limiting factor on where we can use FRP. But obviously, you need to take great care as a designer. We've also done some experimental work to prove that the connections themselves are probably more ductile than you might think, despite the material itself being somewhat brittle. And then in regard to fire, there are some references. There are ASTM standards for testing FRP components. The IBC chapter for plastics, which is chapter 26, should know this off the top of my head. Sorry if I've screwed it up, but it's somewhere in the 20s. Is largely dedicated to cladding because a lot of high-rise buildings have been clad with some sort of composite material over the years. So the IBC chapter on plastics is almost entirely devoted to fire standards, and those are the ones that you would need to follow. There's less guidance in the LRFD. Again, that's really focused on structural load application, but there's a few references in there, particularly to when you have sustained load and sustained temperatures. That's where you have to be very careful as a designer. Just to further validate what David said.
Great. Thank you, Kevin. And our next question is, are there any courses for new engineers to learn how to design with FRP Pultruded structures? Does any of the University of Miami or Notre Dame are offering any courses?
Kevin, you guys offering anything up there?
We offer at the moment a lightweight structures course, which quickly covers FRP wood and light gauge steel. Just in the interest of time, I would love to offer a full 3 credit hour dedicated semester long course just to Pultruded FRP. We have more resources than we would need to teach that. We could teach 2 or 3 levels of it, but just based on curriculum restraints at the moment, we can only fit it into a part of a class. I'm not aware of any university that teaches a whole dedicated course to Pultruded FRP. The truth is there's at the moment, despite its growth in the AEC industry, there's not a lot of structural engineering firms that are comfortable with designing it. So I know that our team, in collaboration with Francisco's team at University of Miami and some other industry players, are going to be launching some road shows in the next year, sharing design examples, guidelines for designing FRP. And Aparna, I'll let you speak to that further if you'd like.
Yeah, if I can add, I think as part of this project also, we are publishing a design manual for pultruded structures that will have design examples covering connections, columns, and beams that are specific and going detail both for ASCE as well as the European ones, and looking at the differences as well as explaining fundamentals. Obviously, this is sort of like a learning. There's many books out there. And I think I would also add that many of the manufacturers, and maybe this is the caveat, right? There's no standardization, or there's little standardization today on your sections and whatnot. And you sort of look up tables provided by the manufacturers of what sections they have and what capacities they have. So you're sort of granted this information versus being able to sort of calculate it. So many times, I think up to today, right, you guys have been relying on that information and giving that. I think with with the LRFD now, we'll start moving closer to standardization that will require engineers to understand, what is the material that I'm getting, and I think that will broaden up, right, rather than having customized each one doing their own thing with their, because we haven't really talked. The FRP has multiple layers of those glass fibers in different orientations to form that thickness of those structural shapes, and I think that's part of the ingenuity of the different manufacturers of making those elements. But I think there's a synergy and a consensus of moving forward. But as of today, I think it's not like sign up for here. I think we can certainly put one together, but it is highly specialized and it's sort of a demand and supply type of thing, right? Today, the demand is little, so there's very little supply for it. But I'm sure that within the near future, there'll be an increase in this as we move forward.
At University of Delft in Netherlands offer the online course, but it is based on the Eurocode. Each year, in the Netherlands.
Yeah, that's great to know. Yeah. So as I want to add what Kevin and Francisco was saying, that next is here to advocate more about composite, how to design with it. And so we already have a guideline which was developed by Francisco's group, University of Miami, which is focused on selection guideline for FRP Pultruded structures, which is a free download, which is available for free download on next website. They are also working, Kevin's group and Francisco's group is also working on design examples, which will be complementary to ASCE 74. So I think we are there. We are working on it. So all the education products will be available soon for you to take a course or to learn how to design with Pultruded. With this, we have one last question. I just want to take that. How is the FRP Pultruded availability in United States? How is the market and will it grow? Is there a shortage, or will it grow as time as per the project needs?
I'll start by answering, but David, having had a recent conversation with some manufacturers, can chime in. It's growing. Most of the materials are domestically supplied. All the manufacturing is domestic. One reason that FRP has been specified in some of our projects is based on its availability and the speed in which it can be fabricated and shipped versus some of the other contemporary materials. The industry is very interested in growing the construction sector. Obviously, its history is in maritime and aerospace, and understandably so. But the construction sector is just so much bigger. In terms of the standard polyester glass or e-glass products, we have not run into any availability problems that I'm aware of on any projects. When we have needed a more specialized resin like vinyl ester, then we've had to be a bit more inventive with what sections we're specifying, just because there's limited inventory. But for the standard polyester pultruded shapes, they're pretty readily available, and those companies can ramp up very quickly. The nature of how it's manufactured is such that they can produce it really, really quickly. They just need the demand there.
Okay.
And they're seeing more of it.
Yeah. Just to add on it, as I was mentioning before, there is a movement towards standardization of those sections, so you can find similar sections that are readily available through multiple manufacturers. Someone that, if you are interested in specifying FRP, might want to keep in mind is that most manufacturers, they also have an availability list, meaning that they are explicitly saying which are the sections and which are the profiles that they keep in stock regularly, so that if you ask for them, it will be ready to ship basically the day after. While if you need customized shapes or you need something that is not in stock, depending on the demand of the project, meaning how big is the project, they might start pultruding right away. And as you see, the pultrusion is a process that can run 24/7. Basically, so even if they are not in stock, it would be fast to to manufacture it if the demands and the required material is enough to justify the expense for the manufacturer. And if not, you can define a solution with the profiles that they keep in stock that are extensive in terms of quantities and selection.
Great. Thank you so much. Thank you for answering all the questions. We had a very good panel of speakers here, and it was a wonderful presentation. Thank you for sharing all your insight. And with this, we have some few more slides, just information. So we have upcoming webinars. These are the upcoming webinars for December and January. Please register on ACI website to attend these webinars. And thank you all for participating in this webinar, and see you next time. Thank you.
Thank you, everybody.
Thank you, everyone.